Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 3rd, 2026, just 3 days ago. It demonstrates how Google's Gemini DeepThink model successfully acted as a co-author to refute a decade-old mathematical conjecture and identify fatal flaws in cryptographic proofs that human reviewers missed. The paper is titled Accelerating Scientific Research with Gemini, Case Studies and Common Techniques. And as we'll see in the case studies later, the model's ability to act as a rigorous adversarial reviewer has huge implications for the future of scientific discovery. To understand how this collaboration works, Figure 1 illustrates the reasoning architecture. It begins with a human researcher providing a problem statement to the Gemini agent. The model then performs an extensive exploration of the solution space, visualizing this as a branching tree of possibilities rather than a single linear path. This is followed by deep reasoning and, finally, a rigorous stage of automated and human verification. If flaws are found, the feedback loop on the right allows the agent to iterate and refine its solution. Well, Figure 2 illustrates one of the model's most powerful capabilities, cross-pollination. Here, the diagram shows how the AI tackled a complex optimization problem. On the left, the issue is represented in its original domain of discrete combinatorics, involving a set of unit vectors. The model successfully reframed this, as shown by the central arrow, into a continuous energy minimization problem on the right. By shifting the perspective to continuous probability measures, the AI unlocked advanced tools like the Stone-Weierstrass theorem, which were previously inapplicable. So, continuing with these examples, panel B illustrates a solution for the simplex is best conjecture in Euclidean Steiner trees. On the left, the diagram starts with an arbitrary graph embedding in orange. The model constructed a specific mapping to transform this into the star graph on the right, which forms a regular geometric simplex. The key innovation is highlighted in the center. The AI recognized this as a distance-compressing map and applied the Kersbron extension theorem, effectively proving that the transformation preserves the necessary cost bounds. Alright, transitioning to the realm of online algorithms, Table 1 presents this specific counterexample that refuted the 2015 conjecture. It defines valuation functions for a minimal instance involving just 3 items, labeled E, X1, and X2. The first column lists every possible subset of these items, while the remaining columns assign specific numerical values to each group. Crucially, the final column, V1, includes a precise perturbation that shifts the values just enough to violate the theoretical bound. Now, Figure 3 details the specific adversarial prompting strategy that enabled the model to find the fatal flaw in the SNARG paper. Instead of a simple request to check the proof, the authors enforced a rigorous 5-step loop. It starts with an initial objective review, but then, in step 2, the model must critique its own findings to filter out hallucinations. This process iterates, generating a revised review, self-correcting a second time, and only then producing the final verified output. Well, leaving the cryptography examples behind, Table 2 highlights a major success in theoretical physics regarding the evaluation of cosmic string radiation. The first 3 methods listed at the top relied on monomial expansions, which failed due to catastrophic numerical instability. In contrast, the final row reveals the breakthrough, Method 6. Here, the AI derived a Gegenbauer expansion, which achieves constant time complexity and provides a completely stable, exact analytic closed-form solution. So, wrapping up, the big takeaway is that models like Gemini DeepThink are transitioning from simple assistants to genuine co-authors capable of novel mathematical discovery. By bridging disciplines and spotting subtle errors, they are fundamentally reshaping the scientific process. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.